trivial questions sometimes require deep and expansive knowledge of the cosmos just to answer them. In middle school chemistry class, I asked my teacher where the elements on the periodic table come from. He replied, "Earth's crust." I'll grant him that. It's surely where the supply lab gets them. But how did Earth's crust acquire them? The answer must be astronomical. But in this case, do you actually need to know the origin and evolution of the universe to answer the question? Yes, you do. Only 3 of the naturally occurring elements were manufactured in the Big Bang. The rest were forged in the high-temperature hearts and explosive remains of dying stars, enabling subsequent generations of star systems to incorporate this enrichment, forming planets and, in our case, people. For many, the periodic table of chemical elements is a forgotten oddity, a chart of boxes filled with mysterious, cryptic letters last encountered on the wall of high school chemistry class. As the organizing principle for the chemical behavior of all known and yet to be discovered elements in the universe, the table instead ought to be a cultural icon, a testimony to the enterprise of science as an international human adventure conducted in laboratories, particle accelerators, and on the frontier of the cosmos itself. Yet every now and then, even a scientist can't help thinking of the periodic table as a zoo of one-of-a-kind animals conceived by Dr. Seuss. How else could we believe that sodium is a poisonous, reactive metal that you can cut with a butter knife, while pure chlorine is a smelly, deadly gas, yet when added together they make sodium chloride, a harmless, biologically essential compound better known as table salt? Or how about hydrogen and oxygen? One is an explosive gas, and the other promotes violent combustion, yet the two combined make liquid water, which puts out fires. Amid these chemical confabulations we find elements significant to the cosmos, allowing me to offer the periodic table as viewed through the lens of an astrophysicist. With only one proton in its nucleus, hydrogen is the lightest and simplest element, made entirely during the Big Bang. Out of the 94 naturally occurring elements, hydrogen lays claim to more than 2/3 of all the atoms in the human body, and more than 90% of all atoms in the cosmos, on all scales, right on down to the solar system. Hydrogen in the core of the massive planet Jupiter is under so much pressure that it behaves more like a conductive metal than a gas, creating the strongest magnetic field among the planets. The English chemist Henry Cavendish discovered hydrogen in 1766 during his experiments with H2O. Hydrogenes is Greek for water forming, but he is best known among astrophysicists as the first to calculate Earth's mass after having measured an accurate value for the gravitational constant in Newton's famous equation for gravity. Every second of every day, 4.5 billion tons of fast-moving hydrogen nuclei are turned into energy as they slam together to make helium within the 15 million degree core of the Sun. Helium is widely recognized as an over-the-counter, low-density gas that, when inhaled, temporarily increases the vibrational frequency of your windpipe and larynx, making you sound like Mickey Mouse. Helium is the second simplest and second most abundant element in the universe. Although a distant second to hydrogen in abundance, there's 4 times more of it than all other elements in the universe combined. One of the pillars of Big Bang cosmology is the prediction that in every region of the cosmos, no less than about 10% of all atoms are helium, manufactured in that percentage across the well-mixed primeval fireball that was the birth of our universe. Since the thermonuclear fusion of hydrogen within stars gives you helium, some regions of the cosmos could easily accumulate more than their 10% share of helium, but, as predicted, no one has ever found a region of the galaxy with less. Some 30 years before it was discovered and isolated on Earth, astronomers detected helium in the spectrum of the Sun's corona during the total eclipse of 1868. As noted earlier, the name helium was duly derived from Helios, the Greek sun god. And with 92% of hydrogen's buoyancy in air, but without its explosive characteristics, helium is the gas of choice for the outsized balloon characters of the Macy's Thanksgiving Day Parade, making the department store second only to the US military as the nation's top user of the element. Lithium is the third simplest element in the universe, with 3 protons in its nucleus. Like hydrogen and helium, lithium was made in the Big Bang, but unlike helium, which can be manufactured in stellar cores, lithium is destroyed by every known nuclear reaction. Another prediction of Big Bang cosmology is that we can expect no more than 1% of the atoms in any region of the universe to be lithium. No one has yet found a galaxy with more lithium than this upper limit supplied by the Big Bang. The combination of helium's upper limit and lithium's lower limit gives a potent dual constraint on tests for Big Bang cosmology. The element carbon can be found in more kinds of molecules than the sum of all other kinds of molecules combined. Given the abundance of carbon in the cosmos forged in the cores of stars, churned up to their surfaces, and released copiously into the galaxy, a better element does not exist on which to base the chemistry and diversity of life. Just edging out carbon in abundance rank, oxygen is common, too, forged and released in the remains of exploded stars. Both oxygen and carbon are major ingredients of life as we know it. But what about life as we don't know it? How about life based on the element silicon? Silicon sits directly below carbon on the periodic table, which means, in principle, it can create the same portfolio of molecules that carbon does. In the end, we expect carbon to win because it's 10 times more abundant than silicon in the cosmos. But that doesn't stop science fiction writers, who keep exobiologists on their toes, wondering what the first truly alien, silicon-based life forms would be like. In addition to being an active ingredient in table salt, at the moment, sodium is the most common glowing gas in municipal street lamps across the nation. They burn brighter and longer than incandescent bulbs, although they may all soon be replaced by LEDs, which are even brighter at a given wattage, and cheaper. Two varieties of sodium lamps are common: high-pressure lamps, which look yellow-white, and the rarer low-pressure lamps, which look orange. Turns out, while all light pollution is bad for astrophysics, the low-pressure sodium lamps are least bad because their contamination can be easily subtracted from telescope data. In a model of cooperation, the entire city of Tucson, Arizona, the nearest large municipality to the Kitt Peak National Observatory, has, by agreement with the local astrophysicists, converted all its streetlights to low-pressure sodium lamps. Aluminum occupies nearly 10% of Earth's crust, yet was unknown to the ancients and unfamiliar to our great-grandparents. The element was not isolated and identified until 1827 and did not enter common household use until the late 1960s, when tin cans and tin foil yielded to aluminum cans and, of course, aluminum foil. I'd bet most old people you know still call the stuff tin foil. Polished aluminum makes a near-perfect reflector of visible light and is the coating of choice for nearly all telescope mirrors today. Titanium is 1.7 times denser than aluminum, but it's more than twice as strong. So titanium, the ninth most abundant element in Earth's crust, has become a modern darling for many applications, such as military aircraft components and prosthetics that require a light, strong metal for their tasks. In most cosmic places, the number of oxygen atoms exceeds that of carbon. After every carbon atom has latched onto the available oxygen atoms, forming carbon monoxide or carbon dioxide, the leftover oxygen bonds with other things, like titanium. The spectra of red stars are riddled with features traceable to titanium oxide, which itself is no stranger to stars on Earth. Star sapphires and rubies owe their radiant asterisms to titanium oxide impurities in their crystal lattice. Furthermore, the white paint used for telescope domes features titanium oxide, which happens to be highly reflective in the infrared part of the spectrum, greatly reducing the heat accumulated from sunlight in the air surrounding the telescope. At nightfall, with the dome open, the air temperature near the telescope rapidly equals the temperature of the nighttime air, allowing light from stars and other cosmic objects to be sharp and clear. And, while not directly named for a cosmic object, titanium derives from the Titans of Greek mythology. Titan is Saturn's largest moon. By many measures, iron ranks as the most important element in the universe. Massive stars manufacture elements in their core, in sequence from helium to carbon to oxygen to nitrogen, and so forth, all the way up the periodic table to iron. With 26 protons and at least as many neutrons in its nucleus, iron's odd distinction comes from having the least total energy per nuclear particle of any element. This means something quite simple: if you split iron atoms via fission, they will absorb energy. And if you combine iron atoms via fusion, they will also absorb energy. Stars, however, are in the business of making energy. As high-mass stars manufacture and accumulate iron in their cores, they are nearing death. Without a fertile source of energy, the star collapses under its own weight and instantly rebounds in a stupendous supernova explosion, outshining a billion suns for more than a week. The soft metal gallium has such a low melting point that, like cocoa butter, it will liquefy on contact with your hand. Apart from this parlor demo, gallium is not interesting to astrophysicists, except as one of the ingredients in the gallium chloride experiments used to detect elusive neutrinos from the sun. A huge, 100-ton, underground vat of liquid gallium chloride is monitored for any collisions between neutrinos and gallium nuclei, turning it into germanium. The encounter emits a spark of X-ray light that is measured every time a nucleus gets slammed. The long-standing solar neutrino problem, where fewer neutrinos were detected than predicted by solar theory, was solved using telescopes such as this. Every form of the element technetium is radioactive. Not surprisingly, it's found nowhere on Earth except in particle accelerators, where we make it on demand. Technetium carries this distinction in its name, which derives from the Greek teknetos, meaning artificial. For reasons not yet fully understood, technetium lives in the atmospheres of a select subset of red stars. This alone would not be cause for alarm, except that technetium has a half-life of a mere 2 million years, which is much shorter than the age and life expectancy of the stars in which it is found. In other words, the star cannot have been born with the stuff, for if it were, there would be none left by now. There is also no known mechanism to create technetium in a star's core and have it dredge itself up to the surface where it is observed, which has led to exotic theories that have yet to achieve consensus in the astrophysics community. Along with osmium and platinum, iridium is one of the three heaviest, densest, elements on the table. 2 cubic feet of it weighs as much as a Buick, which makes iridium one of the world's best paperweights, able to defy all known office fans. Iridium is also the world's most famous smoking gun. A thin layer of it can be found worldwide at the famous Cretaceous Paleogeny, KPG, boundary in geological strata, dating from 65 million years ago. Not so coincidentally, that's when every land species larger than a carry-on suitcase went extinct, including the legendary dinosaurs. Iridium is rare on Earth's surface but relatively common in 6-mile metallic asteroids, which, upon colliding with Earth, vaporize on impact, scattering their atoms across Earth's surface. So, whatever might have been your favorite theory for offing the dinosaurs, a killer asteroid the size of Mount Everest from outer space should be at the top of your list. I don't know how Albert would have felt about this, but an unknown element was discovered in the debris of the first hydrogen bomb test in the Eniwetok Atoll in the South Pacific, on November 1, 1952, and was named Einsteinium in his honor. I might have named it Armageddonium instead. Meanwhile, 10 entries in the periodic table get their names from objects that orbit the Sun. Phosphorus comes from the Greek for light-bearing, and was the ancient name for the planet Venus when it appeared before sunrise in the dawn sky. Selenium comes from Selene, which is Greek for the moon, named so because in ores, it was always associated with the element tellurium, which had already been named for Earth, from the Latin tellus. On January 1, 1801, the Italian astronomer Giuseppe Piazzi discovered a new planet orbiting the Sun in the suspiciously large gap between Mars and Jupiter. Keeping with the tradition of naming planets after Roman gods, the object was named Ceres, after the goddess of harvest. Ceres is, of course, the root of the word cereal. At the time, there was sufficient excitement in the scientific community for the first element to be discovered after this date to be named Cerium in its honor. 2 years later, another planet was discovered, orbiting the Sun in the same gap as Ceres. This one was named Pallas, for the Roman goddess of wisdom, and, like cerium before it, the first element discovered thereafter was named palladium in its honor. The naming party would end a few decades later. After dozens more of these planets were discovered sharing the same orbital zone, closer analysis revealed that these objects were much smaller than the smallest known planets. A new swath of real estate had been discovered in the solar system, populated by small, craggy chunks of rock and metal. Ceres and Pallas were not planets, they are asteroids, and they live in the asteroid belt, now known to contain hundreds of thousands of objects, somewhat more than the number of elements in the periodic table. The metal Mercury, liquid and runny at room temperature, and the planet Mercury, the fastest of all planets in the solar system, are both named for the speedy Roman messenger god of the same name. Thorium is named for Thor, the hunky, lightning bolt, wielding Scandinavian god, who corresponds with lightning bolt, wielding Jupiter in Roman mythology. And by Jove, Hubble Space Telescope images of Jupiter's polar regions reveal extensive electrical discharges deep within its turbulent cloud layers. Alas, Saturn, my favorite planet, has no element named for it, but Uranus, Neptune, and Pluto are famously represented. The element uranium was discovered in 1789 and named in honor of the planet discovered by William Herschel just 8 years earlier. All isotopes of uranium are unstable, spontaneously decaying to lighter elements, a process accompanied by the release of energy. The first atomic bomb ever used in warfare had uranium as its active ingredient, and was dropped by the United States, incinerating the Japanese city of Hiroshima on August 6, 1945. With 92 protons packed in its nucleus, uranium is widely described as the largest naturally occurring element, although trace amounts of larger elements can be found naturally where uranium ore is mined. If Uranus deserved an element named in its honor, then so did Neptune. Unlike uranium, however, which was discovered shortly after the planet, Neptunium was discovered in 1940 in the Berkeley cyclotron, a full 97 years after the German astronomer John Gall found Neptune in a spot in the sky predicted by the French mathematician Joseph Le Verrier after studying Uranus's odd orbital behavior. Just as Neptune comes right after Uranus in the solar system, so too does Neptunium come right after uranium in the periodic table of elements. The Berkeley cyclotron discovered, or manufactured, many elements not found in nature, including plutonium, which directly follows Neptunium in the table and was named for Pluto, which Clyde Tombaugh discovered at Arizona's Lowell Observatory in 1930. Just as with the discovery of Ceres 129 years earlier, excitement prevailed. Pluto was the first planet discovered by an American and, in the absence of better data, was widely regarded as an object of commensurate size and mass to Earth, if not Uranus or Neptune. As our attempts to measure Pluto's size became more and more refined, Pluto kept getting smaller and smaller. Our knowledge of Pluto's dimensions did not stabilize until the late 1980s. We now know that cold, icy Pluto is by far the smallest of the 9, with the diminutive distinction of being littler than the solar system's 6 largest moons. And like the asteroids, hundreds more objects were later discovered in the outer solar system with orbits similar to that of Pluto, signaling the end of Pluto's tenure as a planet, and the revelation of a heretofore undocumented reservoir of small icy bodies called the Kuiper belt of comets, to which Pluto belongs. In this regard, one could argue that Ceres, Pallas, and Pluto slipped into the periodic table under false pretenses. Unstable weapons-grade plutonium was the active ingredient in the atomic bomb that the United States exploded over the Japanese city of Nagasaki, just 3 days after Hiroshima, bringing a swift end to World War II. Small quantities of non-weapons-grade radioactive plutonium can be used to power radioisotope thermoelectric generators, sensibly abbreviated as RTGs, for spacecraft that travel to the outer solar system, where the intensity of sunlight has diminished below the level usable by solar panels. 1 pound of plutonium will generate 10 million kilowatt-hours of heat energy, which is enough to power an incandescent light bulb for 11,000 years, or a human being for just as long if we ran on nuclear fuel instead of grocery store food. So ends our cosmic journey through the periodic table of chemical elements, right to the edge of the solar system, and beyond. For reasons I have yet to understand, many people don't like chemicals, which might explain the perennial movement to rid foods of them. Perhaps sesquipedalian chemical names just sound dangerous. But in that case we should blame the chemists, and not the chemicals themselves. Personally, I am quite comfortable with chemicals, anywhere in the universe. My favorite stars, as well as my best friends, are all made of them.